All right, let's dive into one of the most fascinating challenges in all of artificial intelligence. How exactly do we teach a machine to accurately describe what it sees in an image? Now, I know it sounds simple to us, but for a computer, bridging that huge gap between raw pixels and natural flowing human language is a monumental task.
Take a look at this. Think about how instantly you can process the scene. You just look at it and boom, you immediately think, that's a red fire truck sitting in the street. Your brain automatically identifies the objects, understands how they relate to each other, and strings together a perfectly grammatical sentence without you even breaking a sweat. It's effortless.
So the real question for us is, how on earth does a machine learn to formulate a sentence like that? And honestly, why do they so often fail, sometimes in incredibly hilarious and nonsensical ways? Because to get an AI to speak about what it sees, we have to teach it both vision and language at the exact same time.
Here is our roadmap for this explainer. We'll start with the AI captioning problem. Then we'll look at grading the AI, the SPIDEr metric solution, looking ahead with rollouts, and finally, the human verdict. Let's get right into it.
Section 1. The AI captioning problem. Let's look at the basic architecture. Okay, so this brilliantly illustrates what we call the standard show-and-tell model. It works in two main stages. Over on the left, you've got a convolutional neural network, or CNN, which basically acts as the eyes, crunching the image into a dense set of mathematical features. It then tosses that information over to our recurrent neural network, or RNN, on the right. The RNN acts as the mouth, taking those visual cues and generating a sentence, word by single word.
Traditionally, we've trained these models using something called maximum likelihood estimation, or MLE. But here's where it gets really tricky. During training, MLE holds the AI's hand. If the AI guesses the first word wrong, MLE steps in and feeds it the correct ground truth word anyway, so it can guess the second word. It's literally like having training wheels on, but during testing, the training wheels come off. The AI is fed its own messy predictions. So if it makes one tiny mistake early on in the sentence, it gets confused, it panics, and the errors just snowball. We call this exposure bias. It wanders completely off the right path.
Moving on to Section 2, grading the AI. Let's talk about evaluating performance.
The crucial thing to remember is that an AI is only as good as the grading rubric we use to evaluate it. For a long time, the standard was the BCMR metrics, things like BLEU or CIDEr. Now, these are fantastic at checking for syntactic fluency and grammar, but they have a massive flaw. They don't really care about actual meaning, so they correlate very weakly with how a human would judge the sentence. To fix this, researchers introduced SPICE. SPICE is brilliant at checking semantic meaning, like did the AI identify the right objects? But SPICE has a fatal flaw too. It completely ignores grammar.
To really see this in action, let's look at this scene. What happens when you train an AI and tell it, hey, I only care about your SPICE score. Just give me the meaning, grammar doesn't matter at all. Well, you get something like this. The SPICE-optimized AI spits out a group of people walking down a street with a man on a street holding a traffic light and a traffic light on a city street with a city street. Right? It is a hilariously repetitive, stuttering mess. I mean, sure, it correctly identified the people, the street, the traffic light, so it scored high on meaning. But because the SPICE rubric never penalized it for bad syntax, it just kept babbling.
Which brings us to Section 3, the SPIDEr metric solution, getting the best of both worlds.
Researchers realized they absolutely needed the best of both worlds. Enter SPIDEr. It's this beautifully simple supermetric. It's basically a linear combination of SPICE and CIDEr. It takes the semantic faithfulness of SPICE, ensuring the AI is actually talking about what's in the image, and seamlessly combines it with the syntactical fluency of CIDEr, making sure the sentence is actually readable. When you grade an AI with SPIDEr, high scores finally translate to high-quality, human-approved ratings.
Section 4, looking ahead with rollouts.
Now, actually optimizing this new, complex SPIDEr score required a totally different approach. Traditional training just had the AI guess the next word blindly. But here, researchers implemented a chess-like training method using policy gradients with Monte Carlo Rollouts. Notice those branching blue paths? Instead of just blurting out a word, the AI actually pauses. It looks at the potential next word and then plays out the rest of the sentence in its head multiple times. It's essentially asking itself, okay, if I say the word fire right now, will that eventually lead to a high SPIDEr score at the end of the sentence?
So the logic flows like this. Step 1, the AI chooses a potential next word. Step 2, it runs those Monte Carlo rollouts, sampling several possible ways the rest of the sentence could play out. Step 3, it calculates the average SPIDEr reward of those imaginary completed sequences. And finally, step 4, it uses that expected future reward to optimize its choice in the present. It literally learns what works best by simulating the future. Now, why is this such a game changer? Well, previously, researchers tried a method called Mixer to achieve a similar goal, but honestly, it was highly unstable. It required this agonizingly delicate balancing act, slowly transitioning from MLE training to policy gradient training over millions of steps. This new Monte Carlo rollout approach entirely sidesteps that messy mix. It evaluates the future directly, which leads to much faster, incredibly stable training convergence. It is simply a vastly superior way to teach the network.
Finally, Section 5, the human verdict. Let's see what real people thought.
Let's loop back to that very first image of the fire engine. When graded by the old traditional MLE model, the AI confidently declared, "A red and white bus is driving down the street." A bus. It completely hallucinated that because of that exposure bias we talked about earlier. But look at our new model, trained with policy gradients, Monte Carlo rollouts, and the SPIDEr metric. It says, "A red fire truck is on a city street." It completely nailed it. And this wasn't just a one-off lucky guess either. When researchers took this model and put it to the ultimate test, grading by actual human beings on the COCO test set, the results were stunning. The percentage of captions rated by humans as not bad jumped from a 38% baseline using the old methods all the way up to nearly 49% using the SPIDEr metric and rollouts. That is a massive leap in a field where progress is usually measured in tiny fractions of a percent. So what's the big takeaway from this explainer? It's that AI doesn't just get smarter by shoving more data at it. It gets smarter when we give it a better grading rubric and the ability to actually simulate the future. By combining the semantic focus of SPICE with the fluency of CIDEr and empowering it with Monte Carlo rollouts, we've taught the machine to speak with real, human-like clarity. And as these visual language models become even more advanced, it leaves us with a thrilling question. If AI can now see and speak like us, what will it describe next? Thanks for joining me on this deep dive. Keep learning, and I'll see you next time.